Now we're really just going to go straight to questions. So I hope you guys have been thinking of some. I apologize again that we weren't able to have Dr. Ballard and Katie Croft with us to take their questions. But again, do go to nautiluslive.org and submit your questions for the both of them. I think there are microphones, yeah. So we do have a request from the recording that you do wait for, even though we can all hear each other pretty well in this room, that you do wait for the microphone to come to you so that we can actually capture the audio on. Yeah, slide in here, guys. All right, questions.
Thanks. So, Albert, fantastic geophysical data you just showed us there from that exploration of that very remote region. You mentioned earlier in your talk that there was an attempt to gain UNESCO World Heritage Site status for the region, and that further evidence was required. So, with what you captured there, how far along that road have you got? Is that enough evidence? And if you were able to do a more detailed study of that region, perhaps a more invasive one, what evidence would you be able to find, do you think, that would satisfy those criteria?
Well, you know, at this point, the only evidence that's remaining to be found is DNA. You know, we've got the material, we've got the foundation, we've got the dates on those, and we have a good idea of what that temple was used for as a worship location, right? So the last piece of the pie is to say, well, here's DNA from one of the khans. The thing about it is that that doesn't necessarily mean everything, right? But it's almost more important to know about the worshiping traditions, that were done by the people that loved this Khan, throughout the ages, right? So knowing the temple for all of its, uses is remarkable. And I just presented this, to the ambassador of Mongolia at his home in Washington, D.C. a couple of months ago, and we'll be working with the president, and meeting with the president to describe, what we have found. But this is very new, fresh stuff, so we haven't even started. But we are going to hopefully use this to create that site from the Mongolian, agencies, right? This knowledge will be provided from this multi-international collaboration that was done with Mongolian scientists in our lab, and then use that and present it to the government and have help in any way we can that process. But it's going to come from the Mongolian people.
Next question. Got one over here.
Hi. So the sort of exhibitions, the projects that you set out, they're probably like long-term, 5, 10, 20 years kind of thing. How much are they developed with the technology around at the time that you sort of set these in place, and how much do the projects kind of drive the development of the new technology for them?
Actually, why don't you start and then I'll, yeah.
Was that to both of us?
Yeah, I guess both you relevant.
Well, technology is really cool, right? So you try to build things that you can play with at home, like those drones. I just wanted some drones, but I think it's a problem-solving challenge, right? So you face a challenge of a needle in a haystack, and you can't even touch the haystack, kind of challenge, and then you build. You build methods and you trial and error throughout that, and sometimes things are possible and sometimes they're not, but that's the fun part. It's just problem solving. So I think the problem kind of, for me at least, the challenge evolves. Well, the challenge stays the same. The technology that develops evolves over time, and you're able at some critical moments to change strategies because all of a sudden you have way more processing power, or you've got better batteries and things like this that allow you to do things in different ways. But fundamentally, for me, it's a much shorter time frame. I think for Kevin, it's more of a relevant answer probably because they look at these 20-year time frames or more than that, right? And I look at every year we're changing and rebuilding. So
yeah, we definitely operate on different time scales there. Although when I do my field work, I'm using some similar technologies. But when you look at those spacecraft, the Cassini spacecraft and the Galileo spacecraft, typically the technology that makes it to the launch pad is at least a decade old by the time you get to launch. The Galileo spacecraft, for instance, which was operating in the late 90s and the early part of the last decade, that had, for data storage, a magnetic tape recorder on it. And that's because it was designed and built around late 1970s technology that was robust at the time. That said, the flip side of how that technology then feeds into the sort of modern epic of innovation is also interesting. A good example is that the high-gain antenna on the Galileo spacecraft failed to deploy fully. And this was initially seen as a tremendous problem for the spacecraft. Most missions have a high-gain antenna and then a low-gain antenna. And the high-gain antenna is what you use to get your images and most of your data back. And so when that fails and you're constrained to just the low-gain antenna, you are literally sucking data through a very, very tiny straw. And that was a huge challenge. But what ended up happening is that the software engineers and other engineers on the project figured out all sorts of new ways to do data compression and to get that data from the spacecraft back down to Earth through the Deep Space Network. And those data compression algorithms and that research into that problem then fed forward into some of the things that we now use today for streaming online and all that stuff.
JPEGs were actually created. It was the JPEG format that was actually created by that engineer that we use commonly today. Yep.
I was intrigued by the potential of novel life forms, of course. The two questions I had, you did describe the temperature, which sounds like the division rates for any microbes there might be quite spectacularly long. But also, I mean, you also mentioned the fact that we're very carbon-centric, DNA-centric, lipid bilayer-centric. Do you think if we having the technologies to go there and having the technologies to sample, do you think we have the understanding to recognize a life form that doesn't fit our paradigm?
Yeah, that's a great question, and it's one that we debate a lot in my field. And life is sort of a binary thing, right? It's either alive or dead. And to design a mission and an instrument payload suite that would just search for life, I think is kind of fundamentally flawed. But here again, our exploration of Earth and the limits of life on Earth helps guide us, because while we can't necessarily do hypothesis-driven science to find life or not find it, what we can do is develop hypotheses around what it takes for an environment to be habitable. We know that life on Earth operates in a certain pH range, a certain salinity range, a certain temperature range, a certain pressure range, a certain redox chemistry range. Those are metrics that we can then go and study. And so when we design the instrument payloads, I like to do sort of a 2/3, 1/3 bracketing for most of the payload should be hypothesis-driven. But you also want your instruments to have that discovery-driven science capability, because if it is there, you certainly wouldn't want to miss it. Now, part of why we're doing this search is to help us define what the heck life is. We don't have a succinct definition for what life is, and my PhD advisor loves to make the analogy to Da Vinci, trying to define water back in his day. If you look at Da Vinci's notebooks, he describes water as sometimes warm, sometimes cold, sometimes clear, sometimes cloudy. He wraps all these adjectives around it. Fast forward to us now, and thanks to the atomic theory of matter and reductionism, we're able to say that water is H2O. That's it. Are we at a similar place with regard to our definition of life? Right now, all we do is wrap adjectives around it. We don't yet have a succinct definition for what it is. Is reductionism going to get us an answer? I don't think so, because you split life up and you kill it, right? So it's, there's something else going on there from a systems and complexity approach. And so when it comes to defining what life is and what it does, our search for life elsewhere and kind of knowing it when we see it, I think is part of the challenge and part of the task we have to accept in our efforts to try and figure out what life really is. And then with regard to your temperature question, the liquid water on Europa is it's in equilibrium with the ice shell, and so it's slightly below freezing. And the salt that's dissolved in the ocean might suppress the freezing point a bit, but in general, it's a little bit below or hovering around 0 C.
Just a social question as well. Do you find
Just a little social question. This may seem like an extremely loaded question. I don't mean it to be. But do you find that the deeply religious find your work upsetting?
No. Well, I do get those questions. Is this being streamed? Yes. I think it's a wonderful blend. You know, if this is God's universe, what a shame if only a small fraction of it is inhabited. Life is beautiful. That's part of what drives my exploration, whether it's here on Earth exploring the beauty of life or going to these worlds beyond. So on that point, if life is in fact God's creation, why not spread it everywhere?
Another one.
Do you think there's any feasible future for manned space exploration or any advantage that might come from it? It seems like automated vehicles can do a lot, but a lot of the groundbreaking work described for cutting edge work here on Earth has been done by things like James Cameron's manned submersible.
Yeah, the human exploration side serves a phenomenal role when it comes to pushing our own frontier, and from a very practical standpoint, I'm an advocate for it because we need to develop the tools and technology to get ourselves off planet Earth in the event that someday an asteroid hits, et cetera. I think in the sort of very long picture of life, humans will only survive for geological timescales, millions of years, if we do in fact make it out into space, because we will have asteroid impacts and other things. And we're taking the baby steps to do that right now, and it's frustratingly slow. But from the pure science standpoint, when it comes to worlds like Europa, we're not going to send humans there anytime soon. It's too harsh of an environment. When it comes to things like fixing the Hubble Space Telescope, the beauty of the human robot is that we are infinitely programmable and adaptable. Maybe someday we'll have the artificial intelligence and robotic capability to do extraordinarily complex tasks in space, like repair things. But at least for the time being, you're better off training a human being to go in there and get the job done than to build the robot. And the Pathfinder rover, the ones that came before MSL. Steve Squires, who was in charge of the Mars exploration rovers, has on occasion said that the amount of work that some of the simple rovers have done on Mars over the course of years could have been accomplished by a human rover in a matter of minutes to hours. Granted, the cost of getting humans to the surface of Mars is a lot more expensive, but the data return once they're there could potentially be incredible.
I think one of the most interesting things in my experiences with JPL and with working with Katie and Bob is that unmanned doesn't necessarily mean unmanned. So there are drivers driving the Mars Curiosity rover, and when Kevin was talking about the Enceladus flybys, actually meeting the guys who reprogrammed. They had no idea Enceladus was interesting until they got there. So somebody actually had to reprogram Cassini to do those trajectory flybys to actually collect those samples around Enceladus. So there are guys sitting around working that, and they feed that information up. But it's not, these rovers are just sort of going out and doing all the work. And when we're on the ship, or Bob and Katie are finding that shipwreck, yes, they're not physically down on the sub, and we're just sort of floating 3,000 feet above it, but it's as if you're there. And there's a sub pilot, and there's a sub driver, and the ROV just couldn't do it itself. So I think it's sort of this myth that it's purely unmanned. It's just not, we're not physically handling the objects when we're there, which would speed things up if we could do it. But yeah. Next question. Over here.
Yeah, it's just a general question on sort of the practicalities of your missions. They're both obviously fascinating and have their worth. I was wondering if you could enlighten us on how you get funding for these sorts of trips. Who makes the decisions? I'm imagining there were guys sitting around the table saying, do my idea, fund my idea, fund my idea. I mean, how does that process work in both your fields?
They both look, I thought you both looked
well,
at me.
so you've
like,
got you've got a gatekeeper over here and somebody trying to get in there on our end. My funding story is pretty ad hoc, I guess. When I started out this project originally, it was right out of my PhD, and it was purely this just came, it sort of clicked in my head, and I made a plan for this. There was no funding, so I sold everything I had and moved into my car and gave myself 1 year to get funding, and went all in. And by the time that the moment I finally got any kind of support financially for it, my car had been impounded, and I was on my last couch basically, because I didn't have money for the registration. So it's a lot of just full commitment and hope that it works out. I got my first grant through the National Geographic Society, through a philanthropist known as Ted Waite. He was the founder of Gateway, and he supported a lot of exploratory grants within National Geographic and made it possible for me to take my first expedition to Mongolia with a big team. But I had already leveraged all my friends and family for every ounce I could before that, and didn't have a clue of how I was going to pay them back until that grant came through. Now, the granting process for people that are interested in doing work, there's many ways through the National Geographic Society. You just have to write one and submit it, right? But
or know somebody.
or knock on Susan's door and say,
They do that a lot.
Is this a good idea? But it's really fun because the society now has these events where everybody gets together, and it's once a year in Washington, D.C., and you really just start brainstorming with all the other research scientists about how to collaborate in new directions and in new ways, and that's where some of the greatest projects come together. And the synthesis of that energy, I think, is sometimes even facilitated by collaborative grant processes within the society, where they only give grants to teams of multiple explorers, right? So it's a very fun and daunting process, but one of total commitment if you're going to try to do it, I guess. Would you?
Yeah,
Will you sleep on your couch to fund a mission to Europa?
Sleep
in your car.
Long time on the couch.
I'll be passing a hat and juggling out in the square later today. Fund my mission to Europa.
Hey,
but before I should say that a lot of our work is funded by the National Science Foundation as well now. I finally have gotten a couple of NSF grants to support a lot of the computer vision stuff we're doing. So.
Yeah, and I think a lot of impassioned scientists and engineering stories can all, at some point, be traced back to living out of a vehicle. I lived out of a VW bus for many years in grad school, and you got to do what you got to do. When it comes to my research in the lab and field work, I write proposals to NASA. When it comes to the big missions, that is panel after panel after panel, and NASA has got a few different classes of missions. The Discovery class mission is less than $500 million per mission, and JPL just won the most recent mission in that category. It's a mission called InSight, and it's going to land seismometers on the surface of Mars and explore the interior of Mars. So Discovery missions are sort of the smallest class. Then you've got New Frontiers, and then you've got flagship missions. The Galileo and Cassini spacecraft are flagship class missions. These are missions that are not competed. They are assigned by NASA headquarters to various centers to build and put together. These are missions that cost a few $1 billion over the course of the full lifetime. Now, a few $1 billion sounds like a lot, but when you take $2 billion and divide by 20 years, it's actually not that much, especially when you consider what other expenditures are. You know, NASA's annual budget is about $18 billion, and that's everything included, from Earth, astronomy, space, planetary, aviation, et cetera. To give you a frame of reference, how many of you over here are familiar with the Bernie Madoff scandal? You know, yeah, so I like to put things in terms of Madoff units these days. The Bernie Madoff scandal was $60 billion, and so NASA's annual budget is less than a third of a Madoff. And so a lot gets done.
I like that.
A lot gets done with that money. And it pits mission against mission. There was a competition between the flagship mission to Europa and a flagship mission to Titan, both phenomenal worlds to explore. But during that competition, Europa came out on top, and we thought we were going forward with a green light. A year and a half ago, if you had asked me where we would be right now, I would say I'm going to be, you know, machining stuff to get ready for this mission. But then the funding and politics and fiscal situation pulled the rug out from under us, and we're back pushing the ball up the Sisyphean mountain to try and get a new start for the mission in the coming years. So again, whether it's the length of the mission or just getting to the launch pad, it's not for the faint of heart.
Do you see private industry funding planetary expeditions at some point?
Well, as Susan knows, just yesterday, as soon as I got here, the first thing I had to do was telecon back in to San Diego to connect up with James Cameron and the rest of our science team, because we had a science team meeting about the results from the Mariana Trench stuff. And, you know, it's a little side conversation with Jim that I've had on a few occasions is, what's it going to take for us to get private investors to pony up? And I think we're getting there.
He started by making you a sweet animation.
Yes. So he's definitely a fan. But yeah, we're in conversations with various engineers, and if we can do this with private funding, then that may speed up the timescale. The trick is that it really has to be from a philanthropic and altruistic standpoint, because the most amount of money that you're going to get by sending a lander to Europa is the 1.2 or whatever it is, a little over $1 million that you get from winning a Nobel Prize. Because if there is, in fact, life there, then sure, you'll get a Nobel Prize out of it, and that's got some prestige and everything. But other than that, there's not much I can offer the private investor, except cool pictures and revolutionary science. Yeah.
Any more questions? I had one question for the both of you that I think is really interesting, because each of you work across disciplines. And some of the benefits and challenges in that, like you work very closely with archaeologists, and you know, as an engineer, you have to sort of merge those two. It's very, you know, you have the cultural sensitivities, you have all of that, and how that comes together. And you, as well as, you know, working in the, you know, astrobiology field, you're crossing tons of disciplines. And I just wanted you both to speak to that a little bit.
You mean about the multidisciplinary nature of what we're trying to do?
Yeah, what are some of the challenges and benefits?
Well, it's, you know, it's there's always the challenges, but it's not even an argument now that I think that it's the only direction to go in terms of approaching science. You need to have, you know, deep knowledge in certain areas, but have to be very broad in terms of, you know, your cross-disciplinary approach. You know, I think for me, some of the anecdotally funny challenges are, you know, you try to get an archaeologist to even know what a USB cord is sometimes, and you know, really, yeah. But at the same time, an archaeologist, you know, has knowledge about, you know, the historical context of why we're finding things in certain stratifications that, as an engineer, I just never would have imagined or thought of. You know, so, you know, we learn from each other. And the developments of what we're building now are centered around that integral, live together type of process, right? The most exciting times of the innovation that I've had on these projects hasn't been in the lab. The lab has been a really great place. They've actually been in our yurt, because you're stuck in a room that's about the size of this little corner area here with engineers and archaeologists and historians, and you got nowhere to go and no internet connection and nothing to do but because it's been raining for the last 3 days, and you're basically in a big swamp puddle, and all you can do is think about the problems that you're facing and come up with solutions on the fly. And sometimes it's I think we've had to solder together soldering irons to solder another soldering iron together, multiple times to try to fix what we've been breaking, throughout the field, but also to customize things, and that's the funnest process, I think. Just this, just hands-on, multidisciplinary collaboration.
Yeah, working from that, the perhaps most interesting aspect for me is that bridge between the scientists and the engineers. My background is a bit mixed, and that's helped me have a successful career at JPL, where it's primarily an engineering institution, and then the scientists there, we work with the engineers to get the science of the missions done. Before I did my PhD in science, I did a master's in robotics, and that has served me well in that I can dialogue very well with the engineers and work very well with them, because all too often what I see is a tension between the two worlds. Because if you just say to a scientist or a group of scientists, what would you do if we sent you to the surface of Mars or in orbit around Europa? You will end up with an incredible list of measurements and cool things to be done. And then that gets shipped off to the engineers, and the engineers have to design a mission around that, and you end up with not a $2 billion mission, but instead a $10 billion mission. Whereas if you have the engineers say, well, put me in orbit around Europa, they will put a brick in orbit around Europa. And so bridging those two so that we get not a Christmas tree of scientific investigations and objectives that costs way too much, and on the engineering side, we push that bridge so that we don't end up with a cool engineering trick that is not capable of getting much science done. Bringing those worlds together has been an area that I've enjoyed, and one that I think is critical for these missions, to make sure that you optimize for science return while minimizing complexity and the cost.
All right, I think we have time for one more question if there is one. If not, no. All right, well, thank you very much for joining us.